In this section, I'm going to show you a few approximate methods that you can use to analyze indeterminate structure. These approximate methods are mainly used in the preliminary analysis for complicated indeterminate structures, and they are based on some assumptions, hence the different answers are possible. The first concept is called structure analogies. Take this truss structure as an example. I apply concentrate load at some joints, and if I realize that this structure can be viewed very similarly as a simply supported beam as such, then I can do analysis on this beam very easily and then obtain shear force and bending moment diagrams. So these two structures share some resemblance. So I can use the results that I obtained from the simply supported beams and apply onto the truss structure. For instance, if I cut a cross-section between B and C, so I obtain the shear force for that particular cross-section, which is 30 kilonewtons, and I go to the truss structure and then cut a cross-section at the same locations, and then put down all the internal member forces at that particular cross-sections. And I will find out that they will have three forces acting at that particular cross-sections. They are two horizontal forces and one diagonal force. So as these two structures have resemblance, so the shear force of 30 kilonewtons at that particular cross-sections on the beam is going to be applied onto this particular cross-sections at the truss structure. So they have the same shear force, 30 kilonewtons. So this 30 kilonewton is acting downward, and out of the three forces, only the diagonal force, FMC, has vertical component. So as a result, the shear force of 30 kilonewton is going to be resisted by this diagonal force of FMC solely. So it tells us that if I take F time cosine angle, then that should be equal to the shear force of 30. So as a result, I can find the diagonal force magnitudes of 37.5 kilonewton. Similarly, I can go to the middle points cross-sections. If I cut a cross-sections there, I find out that the bending moment at that particular cross-section should be equal to 810 kilonewton meter. So if I go over to the truss structure and then cut cross-sections at the same locations, so that cross-section should have the same bending moment based on the structure analogies. So there are two forces at that particular cross-sections. They are horizontal force of C and horizontal force of T. So this force couple is going to resist the bending moment of 810. So you just take 810 divided by the length of 12 meter, then you get the magnitude of C and T, which is equal to 67.5 kilonewton. So this is a concept called structure analogy. This is another example that utilizes structure analogies concepts to solve the structure. So this is a truss structure with 3 degrees of indeterminacy. If you approximate this structure as a beam, then you can analyze this beam structure very easily. And then you compare these two structures and notice that they are structurally resemblance. So if you cut a cross-section at the same locations and use the shear force on the beam to infer the forces on the cross-sections of the truss. So for instance, this particular cross-section shear force is R1, and there are 4 forces at that particular cross-sections of the truss structure. There are 2 member forces that can resist the vertical shear force. So they are FA and FB. So to further obtain FA and FB, then you can assume whether the structure can take both tension or compressions, or the structure can only take tensions. So we call this stiff members if the members can take both tensions and compressions. So under these conditions, it's very common to assume that they have the same magnitudes. So you can use the conditions to solve for FA and FB. If, on the other hand, the component is weak, that is to say that it does not take compression force, then you can further assume that FB, which is a compression force, is equal to 0. So the shear force V is going to be solely taken up by the force of FA. So next concept I want to introduce is called inflation points. So inflation points are those points come with 0 moments or 0 curvature. They can be considered as internal hinges. So if you can identify those points of inflations early on in your analysis, then you can utilize these inflation points to calculate. For instance, I have a beam clamped on the right-hand side and roller support on the left-hand side. Put a uniform distributed loads of W, and your engineering intuition should tell you that the left side of the beam should have positive curvature. On the other side, the clamp side, the bending moment should be clockwise. So which indicating that close to the ends of the clamp, the curvature is negative. So on the left, I have a positive curvature. On the right, I have a negative curvature. So somewhere in the middle, I should have a point that have 0 curvature. So that is inflation point. Indeed, if you go to a further analysis, you will find out that this is the bending moment diagrams, and there is one point that bending moment actually goes to 0. So that is located at about 1/4 from the right-hand side of the beam. So if you are able to estimate or guess the locations of this inflation point early on in your analysis, then you can just do a free body diagrams on the left part of the structure utilizing this inflation point properties. The inflation point property is you only have shear force but no bending moment. So using that conditions, you can actually calculate the reaction at the left ends of the structure. And then you can carry on with equilibriums to get all the other reaction forces on the right-hand side of the beam. So similarly, this is a clamp beam. It's an indeterminate structure. But if you are able to early on identify or estimate the locations of inflation points, then you can use that information to calculate. So detailed analysis show you that there are 2 inflation points which located at, again, 1/4 from both ends of your beam. So these are the actual inflation point locations. So again, if you can estimate or guess the locations of these inflation points early on in your analysis, you can utilize again these properties of inflation point and do a free body diagrams at the midpoint and then try to get the shear force at the inflation points. Utilizing those shear force information, then you can calculate the rest of the reactions of the structure. So here is a simply supported beam under uniform distributed loads. And this is determinate structure, so shear force bending moment are very easy to establish. And it shows you that this structure actually have 2 inflation points at the ends. Here's another structure which is a clamp beam under uniform distributed loads. And detailed analysis show you actually that there are 2 inflation points located at 0.21 length from both ends of the structures. So we can utilize the concept of inflation point to calculate the frames under vertical loads. So here is 2-story frames under uniformly distributed loads. So let me take a portion of the structure and then enlarge it and show you how we can do approximate analysis using the concept of inflection points. So this portion of the structure is under loading is going to be deformed, and such a deformation is going to be bounded between simply supported conditions and claim conditions. We just saw that simply supported conditions, the inflection point is at the two ends of the support, and the claim conditions, the inflection point is at 0.21 L from both ends of the support. So this boundary conditions is somewhere between simply supported and claim support. So it's common to assume that the inflation points under these conditions occurred at 0.1 L, measuring from both ends of your support. So as a result, we can use these concepts to approximately analyze frames under vertical loads. So let me show you how. So again, let me take out that portions of the frame and then put it here. As we just mentioned, that I'm going to assume that there are two inflation points at this span. So the locations of the inflation point is going to be 0.1 L. L being the length of the span from both ends of the support. So here's the first inflation point, here's the second inflation point. So you can consider the midpoint, the mid portion here as a simply supported beam. So analyzing simply supported beam under uniform distributed loads. So you can get reactions, and then these two reactions is going to act at the remaining part of your frame. So here. So you can analyze this part of your structure deterministically. So if you adopt this concept for the rest of the beams, then you can calculate the reactions, forces inside the frame structure very easily. We can use also this inflation point concept to analyze the conditions when the frame is under horizontal loads. Let me use this single frame structure as an example. So this is 1 bay, 1 story frames, and this structure has 3 degrees of indeterminacies. So if you assume that at the midpoint of each component, there are inflation points, which is internal hinges, then you can analyze this structure deterministically. So you take the upper half of the structure, free body diagrams. These are the inflation points that you assume. Those inflation points carry shear force, axial force, but not bending moments. So what you can do is you can come to either this inflation point or this inflation point and do equilibriums on this free body diagrams. Then you will obtain the vertical force. Then you go to this inflation point, you do a free body diagrams on this left part or right part, then you can get the horizontal force. So after that, you just do equilibriums, and then you get the rest of the two forces. Then you do action reactions. You carry these two forces to the lower part of the structure, and then carry on with your equilibrium analysis. Then you will be able, after that, to plot the bending moment diagrams. Next, I'm going to introduce you to 2 very popular methods that have been developed for analyzing frames under horizontal loads. The first method is called Portal methods. It involved 2 assumptions. The first assumption is the assumptions of inflation points. It assumes that at every midpoint of the component, columns or beams, they are inflection points. The second assumption it adopts is the shear force follow a certain distributions. In fact, it assumes that the individual base inside the frames resist equal amount of horizontal force. So for instance, this is a 3-bay, 2-story frame structure. So the 3 bays at the same story, they resist the same amount of horizontal force. So as a result, the shear force inside this bay, each bay, should have the same amount. But as this inner columns is shared by 2 bay, so the result is the shear force for the inner columns is 2 times of the shear force of the outer columns. So here, this is the Portal methods that people use to analyze frames under horizontal loads. Summarizing, these methods adopt inflection point assumptions. So you put inflection points at every midpoint of the components, including columns and beams. And then it assumes that shear force follow certain distribution. That is, the outer column shear force is 1 time, and the inner column shear force is 2 times. Next is another method that people usually use for analyzing frames under horizontal loads. That is cantilever methods. So the cantilever methods also adopt the same assumptions as the Portal methods, inflection points assumptions. So it assumes that the midpoints of every component has an inflection point. Instead of assuming shear force distributions, the cantilever methods assume axial stresses distributions. It assumes that the axial force of the columns is linearly proportional to the centroids of the columns. So first, you have to locate the centroid of the columns. And then you assume that the axial stress of the columns follow a linear distributions. So because of that, then if you know one axial stress, then you know the other 2 axial stresses. So to execute, you take the axial stresses times the corresponding cross-section area. That gives you the axial force. So to start the analysis, you take the upper half of the structure, put down the axial forces and the shear forces, and you can go to any one of the inflection points and do an equilibrium analysis on these free body diagrams. And because the axial forces are related through this relationship, so there will be only one unknown. So you can calculate the unknown and then obtain all the axial forces that act on these portions of the structure. So after that, then you can use the free body diagrams for any part of the structures and then obtain shear forces and then carry on with your analysis. So this is cantilever methods.